We are recording. Okay, and there we go. All right. All right. Any other questions? I guess I could have recorded that, but I don't have to. Is there any other questions that anybody has from homework from Chapter 8 or Chapter 7 before we kind of start doing some examples? Sorry?
Could you use 6A on the same page?
Same page, 6A? Yeah, okay. I am out of room here, so 6A. All right, I'm going to try something. Can I access the snip tool using this? Type here, SNIP. Yes, snipping tool. New. And copy. Oh, wait, no, cancel. Just shrink that. And, oh, this is actually more of a drag than I thought it was going to be. And then go back to my Onenote. Okay. So you want to do number 6. I'll just do it over here someplace. And how do I get to paste? Anybody much more experienced with tablets than me? Insert. No, it doesn't work. How do I do a right click on a tablet? Oh, good heavens, now I've actually changed books. I didn't mean to do that. Okay, well, this is actually not working the way I thought it would. Like I have it on the clipboard. How do I get to the clipboard when I'm on the tablet? You'd think just hold it. There we go. I didn't hold it long enough. Paste. Ah, I did it. Okay. Obviously, what we want to do with this thing is we want to simplify it into one expression, one logarithm, right? Okay, so what do I have at my disposal? I have my log laws. My log laws tell me that I can combine subtractions into divides and additions into multiply, right? So I'm going to do that first. So this is going to be log to the base 3 of, okay, so the two that add together are multiplies. And the one that subtracts is a divide. There. This is what we've got. And then from there, actually, now that I think about this, that's not the way I want to do it. Nope. Mulligan, I want to redo that. You know what? I've decided. Oh, it's trying to erase. I've decided, actually, I'm going to use the other log law first. You know why I'm thinking that? Because I'm thinking bedmass. Bedmass. And you know what bedmass tells us? It tells us to deal with exponents before divides, multiplies, adds, and subtracts. So I'm going to deal with the exponents first. So I am going to change this to x to the 1/4 so that I don't have any radicals. I have exponents. Then I'm going to deal with my exponents first. And exponents, remember, in logarithms, exponents become coefficients. That's the way to do this. Play the guitar on MTV. There, that's much better looking. Now I'm going to use the law that I was talking about a minute ago, that subtracts become divides. So this minus is going to end up down here. Am I right about this? I'm actually not sure if I'm right about this. 1/4 of log to the base, 1/4 of x, and then this is x times 2x. Now wait a minute, that's not, I'm actually now starting to doubt myself. I'm starting to think maybe I'd have been better off going the way I started. But no, I think not. I think that's the way that this should go. Oh well, we'll see if we get the right answer. So is the right answer log to the base 3 of 2x squared over a quarter x, which means that that's, what's 2 divided by a quarter? Isn't that 8? So that's log to the base 3 of 8x. So what does the answer key say? I don't have an answer key in front of me. Oh, actually, yes, I do. I think I can just scroll down. It'll get to the answer key, won't it? Yeah, there we go. So where are we? 8.2, 8.3, and what number was that? That was 6a. 6a. Oh, no, that's not. You know what? I was right in the first place. And you know what? Now that I think about it, I know why that's right in the first place. Here's why this is wrong. It's bed mass, but these things here aren't part of the argument of the log. Okay, so I need a mulligan on this again. That is wrong. I was right the first time. See that, guys? The only time I'm wrong is when I think I'm wrong. I was right the first time. I can't combine them. I thought I could do a cute little shortcut with exponents, but I can't, because once you turn an exponent into a coefficient, it's not part of the log's argument anymore. So I am going to do this. I'm going to go that's log to the base 3 of x minus log to the base 3 of x to the 1/4 plus log to the base 3 of x squared. Then I'm going to just combine them into one log the way that I thought I would in the first place. So again, the two additions become a multiply, and the subtraction becomes a division. And then I'm going to use my power laws. So this is log to the base 3. Yep, the last way I did it was misguided. So this is actually 1 plus 2, which is 3, and then 3 minus a quarter. And 3 minus 1/4, that's 12 quarters minus 1/4 is 11 quarters. And that is their answer, isn't it? So it's log to the base 3 of x to the 11 quarters. Yep. My mistake on that first attempt was I forgot, I wasn't thinking properly, that once you turn these things here into coefficients, they're not part of the argument of the log anymore, so I can't combine them into one log. So that was the mistake I made. And you know, I've been doing this only 30-something years. You'd think I wouldn't make mistakes like that, but everybody goofs up once in a while. So, sorry about that. All right, maybe one more. Give me a chance to try one without goofing it up. Anything else from, and you don't have to stick to 8.3. Is there anybody who's stuck on anything in 8.1, 8.2? I didn't assign much from 8.2, right? Because we're kind of skipping the graphing stuff. Did I assign anything from 8.2? No, I didn't. We skipped it completely. Or did we? Yeah, we skipped 8.2 completely. But we did do 8.1, right? So is there anybody stuck on anything from 8.1, 8.3, or again, anything in Chapter 7 before we move on to new stuff?
7a of 8.4.
8.4 of, so, okay, hang on, so further on. People watching this on a screen right in front of their face, I hope you're not getting dizzy by me scrolling around. 7, which one again?
7a.
7a, okay, I'm going to just make that smaller for a sec, and then copy it. So it's log of 2x minus 3 plus log of x plus 2 minus 1 equals 0. Okay. There's a couple things we could, there's actually more than one way to approach this question. What we can do is we can combine these two logs together again, since they both have a base of 10, right? I don't have it written there, but I know it's there. Since they have the same base, I can combine them as an argument. So that's log to the base 10 of 2x minus 3 and x plus 2. And I'm going to move the minus 1 to the other side of the equation. Now, I'm going to convert it from a logarithm equation to an exponential equation. So the base of 10 to the exponent of 1 equals the argument of that. And that's how we solve this thing. So now it's our grade 10 and 11 factoring and foiling. So 2x times x is 2x squared. 2x times 2 is 4x. Negative 3 times x is negative 3x. Negative 3 times 2 is negative 6. And then move the 10 to the other side and combine them. So 4x minus 3x is plus x. Minus 6 minus 10 more is minus 16. And can we factor that? Okay, I think we can. 2x squared only breaks up into 2x and x. We could use decomposition for this, but 2x is not very, 2 is not a big number. I'm hoping we can just guess and check our way. We'll Goldilocks this one. 16 and 1 is too big. 8 and 2, I think, is still too far apart. 4 and 4, no, that's not it. Oh, hang on, maybe this doesn't factor. Unless, did I goof something up again? 10 minus from 6, negative 6 minus 10 is negative 16. Oh, that's right. And 4 minus 3, did I goof up? 2 times 2 is 4, 3 times 1 is 3, no? Maybe this doesn't, ugh, guys, maybe that doesn't factor. All right, let's try it by decomposition one time before we give up on factoring. Does 2 times negative 16, which is negative 32, does negative 32 have two factors that are 1 apart? You know what? No, it doesn't. It's got 32 and 1. It's got 16 and 2. It's got 8 and 4. And that's it. Meh. Okay. Is that why this one had you stuck? Because did you get to here? Because guess what we're going to have to use, guys? Grade 11 review. Yeah, when you hit a quadratic that doesn't factor, you've got to use the quadratic formula. So, assuming I didn't copy anything wrong, I'm going to just double check. This doesn't usually happen. 2x minus 3, x plus 2, minus 1. Nope, I didn't copy anything wrong. All right, I'm going to use the quadratic formula. So, x equals minus b plus or minus the square root of b squared minus 4a, oh, hang on, that's a mistake. B squared minus 4ac all over 2a. So that's going to be minus 1 plus or minus the square root of 1 plus 4 times 16 is 64. 64 doubled is 128 over 4. So x is equal to negative 1 plus or minus the square root of 129 over 4. Now, that is the answer for x, but one of them I am very, very sure will be extraneous, namely the negative answer. Oops, I don't know what that is. Go away, editing tips. The negative answer here is going to be extraneous, because remember, the argument of a log can't be negative. So I think that the answer is negative 1 plus the square root of 129 over 4. What do they get? Oh, what number is this? This is 7. Oh, they go to a decimal. Okay, so let's see what that decimal is. I'm punching buttons now. Open a bracket, negative 1 plus the square root of 129, close my bracket, divided by 4, 2.58. Is that their number? Is it 2.58? 2.59. Oh yeah, and if I rounded it, it's 2.59. So yeah, that is the way to do it. They pulled a sneaky on us there. They actually gave us a log one that works out only if you use the quadratic formula. I don't think I've ever seen that. I did see a trig equation once. Actually, I think it was last year. A trig equation popped up on the provincial exam that needed quadratic formula to solve it. But I don't know that I've ever seen that in a log problem on the exam. So I certainly wouldn't do that to you on a test. Anything I give you on the test is going to be factorable. Okay, so you can take that to the bank. If you're getting to this step and it's like, hey, this doesn't factor, something went wrong. Okay, when I test you. Obviously in the real world, yeah, quadratics happen and sometimes they don't factor. All right, I think we should get moving on some new stuff. If you still have questions from homework, message me on Edsby. I'm still gonna, my day isn't that much different, just being online here. I still have a spare, I should call it a prep. You guys call them spares. I have a prep, slot 5, and I'm around at lunch. I'm just going to sit here and eat my lunch and play with my tech. So I can help you out. We could do a quick Teams meeting if you're free, if you're having some homework difficulties. And I don't, again, don't tell my colleagues that I do this, but I don't mind answering your questions even in the evening if I'm sitting by my computer and you pop up on Edsby. So if you're still struggling with homeworky stuff, by all means, we can deal with it later. I'll start tomorrow's class the same way too. I'll ask if there's any questions. But I do want to move on to some new stuff. So we're going to actually go to your chapter, you're going to go to your chapter 7 notes book, and we're going to jump back over to 7.3 applications, because we haven't done that yet. Can everybody get to there? I'll give you a minute. Give you a minute to collect your thoughts and rifle through your binders and find this particular package of notes. And how's my tech holding up? Is everything still working? You can still see my book. You can still see me, in case, again, it's good for your psychology to see my smiling face. Everything good? And my sound still good?
Yep.
Okay, yeah, I don't see any. I have my eye on chat, too, so I have a second screen here so I can see people in the chat. And if you ever do want to say anything to me or ask me a question you don't want other people to see that you're asking me, just message me on Edsby. I won't be able to check Edsby until later, but I will get it. In a few minutes, we'll give people a couple, I mean, we're way into class now, but I'll wait a couple more minutes and then I'll do attendance too. There is a way to download attendance, which is quite exciting. I can do that. Okay. We ready to go? Everybody got to this spot? All right. Exponential functions, like every kind of function we've done this year, have like a standard general form where we can think about them graphically as, let's see, I don't want that. I don't want green, I want yellow. Where yellow? There we go. This is my vertical stretch. This is my horizontal stretch, and of course it has an opposite rule to it. H is my horizontal shift, and K is my vertical shift. Those things have been true for everything we've done this course. They're still true now. So if we did want to spend some time doing some graphing, that tells us how to graph. But we're going to focus on just the algebra and the problem-solving aspects of exponential functions. We already kind of talked about the rice on the chessboard, and we found out that the rice on the chessboard followed the pattern, of course, of there was 1 grain on the first square of the chessboard, then there was 2, then there was 4, then there was 8, there was 16. So really, the formula that tells us how many grains of rice there are on the, what was it, the 64th chessboard piece or place, was y equals 2 to the power of x minus 1. So on the first chessboard, you had 2 to the 0. On the second chessboard square, you had 2 to the 1. Then you had 2 to the 2. Then you had 2 to the 3. But notice, that's kind of the logic I have to use to get an equation. I have to think, okay, well, what's my base here? And then I use that base to build an equation. Here's a good example of the same kind of logic with a more complicated situation. A photographer uses filters to change the look of the photograph she takes. A particular filter reduces the light transmitted through by 15%. So if I lose 15% every time I add a filter, losing 15% means keeping 85%. So think about how this works. If I put no filters on, I have 100% of the light, or 1 of the light. If I put 1 filter on, I now have 85% of the light I had before. Now when I put another filter on, I have 85% of that. So I have 85% of 85%. And if I put another filter on, I have 85% of 85% of 85% of the light that I started with. Do you see where this pattern is going? This number here is 0.85 to the power of 0. This number here is 0.85 to the power of 1. This number here is 0.85 to the power of 2, and of course this point is 0.85 to the power of 3. So when I add no filters, I get 100% of the light. When I add one filter, I get 85% of the light. There's the formula. The amount of light, or the proportion, I should even say the percentage of light, is 0.85 to the power of n. Now, if I wanted to graph that, again, remember that anything to the power of 0 is 1. And then it's going to be a curve up. I know that I'm actually going to get a point here. When n is 1, this will be, what will this be? When n is 1, this will be 0.85. So, yeah, actually, this was a very bad choice for where to put that point. I'm gonna fix that. Oh, whoops. Let's do that again. Let's put 1 up here. There's 1. 0, and then when x is 1, I'm going to get 0.85. So let's say 0.85 is about there. And then when x is 2, I'm going to punch buttons. What is 0.85 times 0.85? You'd think I'd know 85 squared in my head, but I don't. It's 0.7225. So it's only down a little bit more. But then times that by another 0.85, and I get, oh, look at that, I get 0.6 something. And you'll notice what's happening is a curve that way. Right? And again, so this is 1, 0.85, 2, 0.85 squared, 3, 0.85 cubed, and that's going to cause a curve, an upside down exponential curve. Okay. Anybody taking AP Biology? Then hopefully you've seen this before. Actually, this pops up in chemistry as well, talking about radioactive decay. So the half-life of a radioactive substance is 4 days. Write an exponential function that models the proportion p of the substance remaining after t days. So what that means is half-life means that, okay, I start with 100% or 1 of a substance. Then after a certain amount of time, I have half the substance. Then after a certain amount of time, I have half of that. And then after a certain amount of time, I have half of that until I run out of substance. So the half-life means that my base is actually going to be a half. That's why we call it half-life. And notice that T here represents time in days, right? So where does that 4 come from? Well, every 4 days, it would be 1/2 of what I had before. So 4 over 4 would equal 1, and of course a half to the power of 1 would equal a half. So I have a half of what I had before, like that. So use your function to determine the time that must pass until there is 25% of the substance remaining. Well, 25%, let's make our lives easier. 25% is a quarter. So my remaining amount is 1/4. And that's the equation I'm trying to solve. Okay, how do I solve that? Now you're probably going, hey, this is something I could use logarithms on. I could, but we're in chapter 7. We haven't learned logs yet. Can we just solve this just using exponents? And the answer is yes, if we think of a quarter as being a half squared. Everybody remember doing these questions a couple weeks ago? So now that I have the same base here and the same base here, I can make a new equation that says that, oh, that's 5. I don't know why I drew a 5. That's supposed to be a t. Thank you. I can make a new equation that says 2 is equal to t over 4, which means that t is equal to 8, and therefore it takes 8 days. And that's a pretty typical half-life problem. That's an easy one, actually. Also sticking to the biological sciences, bacteria. The number of bacteria in a sample doubles every 10 hours. If they start at 64 colonies present, Well, let's see. Think about the pattern. I start at 64. 10 hours later, I have twice that. 10 hours later, I have twice that. 10 hours later, I have twice that. Give me a formula that represents how much I have after t hours. Remember, every jump here is 10 hours. So that means that I need an exponent of t. This isn't written very well. Make sure that you understand that this t over 10 is an exponent. That's 64 times 2 to the exponent t over 10, right? Because it doubles. So I multiply 64 by 2 when t is 10. Does everybody get where that formula comes from? This is usually where somebody asks, hey, am I ever going to get a question where I have to make that formula? And the answer is, yeah, you could. Every once in a while, one of those did pop up on the provincial where we don't just give you this formula, we give you this information, and you have to figure out the formula. I got a question in the chat that says, will we ever need to do any graphing for Chapter 7 and 8? And the answer is, not in my course. I'm not going to put any graphs on the test. Okay, let's use our function to determine the number of colonies present after 24 hours. This is plug and chug. Plug in 24. Now, before I run this, let's make sure, let's do a quick review of Chapter 7 idea. Here, let's even use a bracket just like the question had. There. Is that, I'm going to give you two choices, people. Is that 18 or is it 36? Now, it's 36 if I go 2 times 3, which is 6, and then square it. Is that what I'm supposed to do? No. It's 18 because BEDMAS says exponents happen before multiplies. So keep that in mind here. This is 64 times 2 to the power of, I guess that's 24 tenths. I guess I could make that 2.4. Make sure you punch that in your calculator properly. I'm going to run that through my calculator. Okay, so that's going to be, hang on. Yeah, okay, sure. 64 times 2 to the power of 2.4. And there we go. I get 337.8. Now, how do you have 0.8 of a colony? You'd probably round that to 338 colonies. Now, there's people going, is there any way, could I have done that without my calculator? And the answer is, well, maybe. Just to show you, I could have thought of it this way. This is maybe advanced technique here. I could have thought of this as 64 times, let me think about this for a sec. 64 times, oh yeah, okay. Nobody would think about it this way if they had a calculator, but let me just write that over here. Oh, wow, why'd I do that? No. 24 over 10 is actually, what is that? That's 10 fifths? 12 fifths. And then 64 is 2 to the power of, I want to say 6, right? 2, 4, 8, 10, yeah, 6. So then what I could do is I could add those exponents together. So 6 plus 12 fifths is 30 plus 12 over 5. So that would be 2 to the power of 42 fifths. And now that I look at that, that's still not something I could do without a calculator. No, but it's going to give me the same answer. I'm going to just double check. 2 to the power of 42, oops, hang on. 2 to the power of, open a bracket, 42 over 5. And, yep, 337.7. So it's the same answer. So I guess what I was maybe saying is, if I had to do this without a calculator, I'd just leave it like that, as a simplified answer of one exponent. Okay? All right. That's just plug and chug, really, right? Put the number into the formula, and out comes the answer. C is algebra, because C, I know that N, and my pen just stopped working. This has happened to me twice today. There you go. It's just glitchy. N is 1024. So that means I have to solve for t. Now I'm going to for sure change 64 to 2 to the power of 6. And 1024, I think, is 2 to the power of 10. So yes, I'm right about that. Now I can say, therefore, 10 is equal to 6 plus t over 10. Isn't that nice? So 10 minus 6 is 4, and t is then 40. And that's 40 hours. There we go. So there's my first word problem, or first couple of word problems for Chapter 7. Next, this is a neat idea. Anybody who's taken accounting, or if you're going to go into the Essential Math program to pick up another credit, you've probably seen this formula. It's called the compound interest formula. Actually, it pops up in Applied, too. So this is one of the few things that you'll see in all three courses. And the compound interest formula, for those of you who don't maybe know how interest works, let's say that I put $100 into the bank. Here, you don't have to write this down if you don't want to. But I put $100 in the bank. Now let's say that I get 10% interest. So that means after whatever the interest period is, I now have 10% of 100 plus 100. Now I could factor that so that I have 100 times 1 plus 10%, right? Now that's my new number, and that's an easy number to figure out. That number is, of course, obviously going to be $110. Now, if my interest is compounded, that means this becomes the new amount that I have in the bank, and my interest now is not based on the original 100 that I started with, but it's based on this number. So now my next calculation is I have 110 times 1.01. So after my next compounding, and this one I'm going to use a calculator for, I have $111.10. And then et cetera, et cetera. So now that becomes my new total in the bank, and then we keep going from there. This can all be represented by this wonderful formula where A is the final amount, P is the how much you put in the first place, R is the interest rate. On the last example I was talking about, it was 10%. N is the number of times it gets compounded in a year. This little t is time in years, and this little n is the same n that is, number of compoundings per year. So this is a fairly complicated formula, but let's see if we can work this through. Kyle invests $1,000 at 3.75% compounded annually. Annually means each year, or once per year is my compounding. So write an exponential function. So the amount is the interest, or the initial money we put in, which is 1,000, times 1 plus, and then it's R, which is my interest rate. Now, I can't use a percent. I have to change that to a decimal, so that's 0.0375. And then, of course, t in this case is annually, so 1 year. So it's over 1. And then this would be to the power of n times t. Well, n is 1, so this is just 1t. So how much is this worth after 7 years? I don't know. All we got to do, though, is put in a 7 for time. Okay. So that's going to be 1,000 times 1.0375 to the power of 7, which is 1293.95. I ran that through my calculator earlier just to save some time. This is an interesting question. Here's my formula. When I don't know t. Okay, actually, I guess, why don't I simplify that formula a bit? So there's my formula. how long will it take the investment to triple in value? Well, wait a minute. Now that I think about it, I actually don't even really know that it says the investment. I guess we mean the 1,000, but it wouldn't matter how much the investment was. Just to triple in value means whatever this number is, times it by 3. So if this was, for example, if this was, suppose I just knew that this was I for initial investment. Oops. What does it mean to triple this number? Oh, it means make it 3I. And then just divide both sides of the equation by I. So that's what I'm going to get. I'm going to get 3 is equal to 1.0375 to the power of t. And if you're thinking, well, hey, you skipped a step there. Yeah, I could have put 3,000 here and have the same formula, and then just divided both sides by 1,000. Ta-da! So that's my formula. Now, here is why I wanted to wait until we did Chapter 8 to do problems like this for Chapter 7. Because your Chapter 7, let me write this a little bigger. Your Chapter 7 strategy for this is, of course, your Goldilocks strategy. You'd put 1.0375 into your calculator, and then you try timesing it. Then you try an exponent of, well, let's try, we know it's more than 7, right? Because we know that we did part B. We don't get anywhere near tripling in 7 years. So let's try 10 years. Let's try 30 years. This one's too small, this one's too big, and you keep playing, keep putting in numbers for t until you get the right answer. But, oh man, what a drag that is. We now have a far more powerful tool than that in our toolbox. I'm not saying there aren't some problems out there that solve really easily and nicely using the Goldilocks technique. Try something smaller, try something bigger, and keep going. This one's too hot, this one's too cold, and then keep going until you find the number that's just right. But we don't need to do that anymore. We can do this with logarithms. We can take the log of both sides of this equation, and remember that exponents become coefficients. And then we can divide both sides of the equation by the log of 1.375. And then we just punch it in our calculator. Do you see now why I wanted to save these problems until we've done Chapter 8? It's so much more efficient this way. So here we go. We have the log, I'm punching buttons on my calculator, 1.0375, sorry, divided by the log of 3, and I get the answer of, hang on a sec, what did I do wrong? Oh, hang on, I did it upside down. Sorry. Let me go back. It's the log of 3 divided by the log of 1. I think I said divide by this number, and then I wrote it down upside down. My apologies. Ooh, I don't have to repunch that in my calculator. I should have a reciprocal button here somewhere. There it is. Dum-da-dum. And I get 29.8 and a bunch of change. Now, here's what I want you to think about. This is a bank, and they compound the interest every year. So I would say that I might as well just say my answer is it takes 30 years. It wouldn't make sense to have a decimal on that. So there you go. Invest a bunch of money at 10%, you'll triple your investment in 30 years. 2 problems with that. Number 1, how many investments stay at an investment rate of 10% and hold that no matter what happens to the market, right? Generally, anything with an interest rate of 10% is something fairly high risk. Chances are it's not gonna hold that over 30 years. Second problem with that is, of course, that anything that is kind of a high return investment, like say a savings bond, they won't let you have it for 30 years. It will mature before, I think most savings bonds mature in 10 years, 15 years. They won't let it go to 30. But in a world where we could invest in things that were secure in a perfect world, this would be true. If you invested at 10%, you would triple your money in 30 years. Does that mean you'd quadruple your money in 40 years? No, it's not a linear equation like that. You could figure out how much it would take. By all means, just do the math again. All right, this might be a good place to take some questions if there are any. One question I've got a couple here that I've noticed. When will our test on Chapter 7 and 8 be? It's going to be next week. I'm going to be I started working on a little bit over the break. I'm putting together a test that we can do in Onenote. And there's people going, oh no, I couldn't get Onenote to work. Then you guys can do it in Edsby. Onenote makes my life so much easier because you don't even have to really submit it. You just put a picture of your work on and I can just mark it right on my tablet here. It's really nice. But if there's people who want to do it in Edsby, you can do it in Edsby. But we're going to try Onenote. But it'll be next week. If you're wondering what that sound is, they're drilling. Again, why they had to do that today, I have no idea, but it's because they aren't smart. Or they don't care about what our jobs are. That's the problem. Other questions I'm getting here. Is there a question-like example in the test? Could be. Yeah. I'd never ask you to memorize this formula. In fact, if you actually look, is it in Chapter 8 or is it in Chapter 7? Maybe it's in Chapter 8. There's a whole page of formulas of the types of situations that are going to use exponential and logarithmic equations. I think the compound interest formula is on it. Actually, this is the last one on here, right? Yeah, so let's go to that page right now. So answering that question for people, are there going to be word problems on the test of this type? Yup. And go to Chapter 8's notes, and you'll see, this is about where we left off right here. Yep. Here is Richter Scale, pH, sound intensity. These are all great things. And here we go. We've given you a reference sheet that you can use for your homework. Obviously, your test will be something similar. If we give you a word problem that involves a science formula or a finance formula, we're going to give you the formula. We don't even make you memorize math formulas. We're not going to make you memorize geology, geography, finance formulas. They're all going to be given to you. So if you were looking at the example we just did and went, oh no, I'm never going to remember formulas, you don't have to. Okay. All right. So there's 8.4 right there. Okay. Any other questions? Is there a time limit on OneNotes, or is it like a submission deadline? I can put a time limit on it. I can have you write the test in slot, what is this, 3, and then I can actually have a time limit on it. I don't know that I will do that though, mainly because I feel bad for anybody who might have some sort of glitch happen in their tech, or their Wi-Fi goes down or something, and then I got to chase them around and give them another test because they've already seen this one. I don't think it's worth my time. I think I'd be happier just to say, all right, for this one time you get a test that doesn't have much of a time limit. So I think there'll be a submission deadline rather than a time limit. I could do it either way, but I'll put a deadline on it. Okay, any other questions before we move on to Chapter 8 stuff? Which, by the way, is going to be the same stuff. It's just got logs instead of just exponents. Okay, right in here. Okay. Go. All right, we ready to go? Everybody on Chapter 8 now? Okay, here we go. Applications Part 1. The Richter Scale. The Richter magnitude M of an earthquake is defined as M equals the log of A over A. You're probably saying A subscript 0. We usually say that as A naught. I don't know if you've ever, and that's an A. That's a very ugly A. Let me fix it. A naught. There we go. So the Richter scale, I have it up there anyway. Okay. I'll get it back to you. Okay, thanks. All right, that was just Mr. T popping in to visit with me. All right, thank you very much. Okay, what was I doing? Oh yeah, so the Richter scale has a magnitude of m, and earthquakes are m equals log of a over a naught, where a is the amplitude of the ground motion, and a naught is the amplitude associated with a standard earthquake. So they gotta compare to a standard earthquake, which is kind of funny. All right, in 1946 in Gwaii, British Columbia, Haida Gwaii, is that really a place? In British Columbia, an earthquake with an amplitude of 10 to the power of 7.7 times a naught struck. Determine the magnitude of this earthquake on the Richter scale. So, my formula is m equals the log of, and then I'll just put the formula down first, a over a naught. Now, what do I know about a? It's this many times a naught. So I'm going to replace that with the log of 10 to the power of 7.7 times a naught. The a naughts cancel, and I have that m is equal to the log of 10 to the 7.7. And remember that the word log without any number here means that the base is 10, right? So if the base is 10, remember that log to the base x of x is always equal to 1, right? But before I do that calculation, use my log law to turn that exponent into a coefficient. And that's a 7.7 on the Richter scale. Any questions on how I did that? I'll keep my eye on the chat here. Okay? All right, that was actually an easy one. Here's a tougher one. Look at B. The strongest recorded earthquake in Haida Gwaii was in 1949, and it was an 8.1. How many times stronger was the 8.1 than the 7.7? Now you're probably going, can I just go 8.1 divided by 7.7? No, because the scale isn't linear, it's logarithmic. Normally you just divide. If I wanted to know how many times bigger is this than that, I just divide those two numbers. That's how many times bigger one of them is than the other. So in this case, my 1949, I'll do this very kind of formally, my 1949 earthquake was 8.1 on the Richter scale, and that of course equals the log of a, okay, now I'm going to use a variable here. I'm going to say that the 1949 earthquake was earthquake X. So this is the amplitude of X, and remember, it's always compared to A naught. So it's always A naught in the bottom. And then I'm going to call the 1946 earthquake, I'm going to call it Y. And earthquake Y was a 7.7 on the Richter scale, and that is equal to the log of the amplitude of Y over, again, they're always compared to some standard earthquake that they call amplitude naught. Now I'm going to change them to exponential form. I'm going to say that, okay, this is an equation, the base is 10, the exponent is 8.1, and the argument is a to the x over a naught. I'm going to do the same thing to the other earthquake from 46. 10 is the base, 7.7 is the exponent, and this is ay over a naught. Okay, from there, I can say that, well, for example, I can say that, that the a to the x here is a naught times 10 to the power of 8.1. And I can say that ay is equal to a naught times 10 to the 7.7. And what did we say a minute ago? How do you determine how many times bigger one thing is than the other? You divide them. So how many times bigger is the big one divided by the small one? So that's a naught times 10 to the 8.1 over A naught times 10 to the 7.7. The A naughts cancel, and then I'm just punching buttons. Actually, I can even make my life a little easier. Remember that when you divide two powers, if they have the same base, you can just subtract their exponents. And that would be, what is 8.1 minus 7.7? That would be 10 to the power of, what would that be? That'd be 0.4. And then I'd need a calculator at this point. I don't know what 10 to the power of 0.4 is. 10 to the power of 1 is 10, so it's smaller than 10. 10 to the power of 0.4 is 2.51. So therefore, the 1949 was 2.51 times stronger than 1946. There we go. Always nice to end word problems with a sentence. All right, I'll keep an eye on the chat here. Any questions on how we did that one? I told you B was a little more complicated than A, but that's how you do that kind of a problem. We have another one similar to that kind of coming up here. In fact, it's very similar. Okay? And actually, you know what? I think I'll save it until tomorrow. So we'll pick it up there tomorrow. You guys have been listening to me now for almost an hour. That's a long time. I'm tired of listening to me. You must be tired of listening to me. So we'll pick it up there tomorrow. So I'm actually not going to assign any new word problems until we finish doing some more examples, especially another example like this guy tomorrow. So let's take a look at what I have on the blog. I kind of knew this was coming. I knew I wasn't going to get through all of these questions today. So go look at the blog. Let's look together. Come on. There we go. So looking at the blog, I even said here, no homework tonight. We'll do more problem examples tomorrow. But if you are somebody who didn't do a whole lot of stuff over the break and there's some stuff in chapters 8.4 part 1 that I assigned, or anything even all the way back to chapter 7 that I've assigned that you haven't caught up on, tonight would be a good chance to maybe get caught up on some homework. I hope your other classes aren't nailing you with a ton of homework on the first day back today. So, and I won't either. This should be stuff that you've hopefully done already. But if you need to catch up a little, we'll give you tonight to catch up before we assign some new word problems. If there's people going, oh, but I'm done all that and I want to work ahead, by all means, flip to the next couple pages. The next page is an example we'll do together. And then there is a reference sheet. And then there's 2 more pages of examples we're going to do together. And then we're going to learn about something called natural log. And then at the very back, there's a page 26 of your booklet. It says word problems. Yay, word problems. Okay, before anybody, don't move, everybody. What I'm going to do is I'm going to flip my book, or my tablet back into a laptop. And I am going to, I'm going to end the meeting in a few minutes here. But before I do, I want to take attendance. So I am going to take attendance for the meeting. Actually, it doesn't really matter if people have left. It records when you leave. So let's see. I go to participants here, and then I go download attendance list. There we go. Now I have attendance. Okay, so I've actually kind of done attendance now. I'll leave my my Teams meeting open for a few minutes here. If you want to ask me any questions or anything, I'll leave the Teams meeting going. But if you've had enough for one day, feel free to log off starting now. Enjoy the rest of your day. Enjoy your lunch, and we'll see you tomorrow. Remember, tomorrow is Wednesday, so we're starting late. Start time tomorrow is 11:29. Okay. All right. Enjoy the rest of your day, guys. Again, if anybody has any questions, I'm going to end the recording.